My name is Janet Mitchell, and these are the justifications for my final. For number one, I chose false because there could be an instance where the point P could be equal to the real number C. So the little counterexample that I have is if P equals 1 and C also equals 1. So you would have to have the less than or equals to in the statement to make it true. For number two, I chose true because the theorem that I found is using open sets, and the statement here uses neighborhoods, but they both define continuity. So I chose true for number two. For number three, I chose false. The theorem here says the supremum and infimum, but the if-then statements says that the compact metric space implies that there are the supremum and infimum points. However, the exam statement has it backwards, and it says that the existence of a supreme point then implies X is compact, which is not true. Okay, here's number four. I chose true for number four. This is about compact sets, and here I drew a little picture. If we have a continuous real function on E that is bounded, then it is compact. And compactness is about being a closed interval and bounded, so the function isn't going off into infinity somewhere. It's kind of like being contained. So I chose four as true. All right, here is number five. I chose false because there's no way f can be continuous at 0. It's saying that f of x and g of x are the same. They are equal everywhere except at 0. But when you take the limits approaching 0 from either side, the limits don't match up. So f can't be continuous at 0. Number six is true. You can see f prime here is e to the x squared over 2. That approaches infinity, so its antiderivative is also going to infinity. That gives us the infinity over infinity, which means we can apply this rule. So we're going to take the second derivative, gives us x e to x squared over 2, and those cancel out, giving us the limit as x approaches infinity, 1 over x, and that does indeed equal 0. So number 6 is true. Number 7, I chose true. I found the theorem 6.4 that has to do with refinements. And I can see equations 9 and 10 here. I drew a little picture so that I could visually see that combining the equations 9 and 10 will give us the difference between the upper and lower limits of P star is less than the upper and lower limits of the P partition. So 7 is true. Number 8 is true. I drew some pictures here because it's saying that for each partition that we put in, it's going to reduce the distance between these partitions, the upper and lower sums, the distance there, it's going to reduce that partition by at most 1/2. So if that is true, then f, this function, is going to be Riemann-Stieltjes integrable. So 8 is true. Number nine is false. I found a very similar homework question. I found that if it's true for f squared to be integrable, that does not necessarily imply that it would be true for f. But the converse statement would be true. If f is integrable, then the higher degrees of f would also be. But for number 9 here, the direction of the statement is not true. Number 10, I said number 10 was false. And for me, it did look very similar to number 5 because number 5 was talking about g of x and it has a jump at 0, but it was implying that f then was continuous, which it isn't. So number 10 here, this is continuous because it is integrable. However, being continuous does not imply that it's differentiable. So when we look at the differentiation here, f prime coming from both directions, they don't match up. So we can't say that f prime at 0 exists. So number 10 is false.